I'll be talking for about 1 hour about Frida hooking on non-jailbroken iOS. This is nothing particularly new. It's just an overview of what we can do right now with what we have. There's no artificial intelligence in this talk. So my name is Francesco Tamagni. I work in NowSecure in the research team with Pancake and Ule. And I contribute to Frida and R2 as much as I can. What I do in the research team is trying to help automating iOS dynamic analysis of applications. That's my GitHub, and those are my nicknames. When the jailbreak is available, Frida takes full advantage of it. But when it's not, it's still possible to use it on iOS with some limitations I'm going to talk about. So I'll be basically in this talk, I will be placing hooks on system library code, but from within the process, the context of an app process, because that's the first limitation. So without jailbreak, that's just what you can attach to. But still, there's the possibility to explore the system library code with at least the part which is reachable from within the app process and the boundaries of it. So I will do this with a lot of help from R2. I already gave this talk in another conference which was shorter, so if you already saw that at the time, this time there will be more R2 into it. I'm gonna do live demos all the time using a simple, stupid test app I wrote, but actually all I talk about will be applicable to any repackaged app in general. So in the live demos, I'll be applying the same hooks to achieve the same result under the 3 different scenarios of increasing difficulty. So the level 0 is the easiest, where the app is launched via debugger. In level 1, we will have no debugger involved, means that we have to launch it manually. That's when you don't have control of the app lifetime when testing it. And the level 2 is still no debugger, but we'll have to deal with pointer authentication. So when we launch an app with a debugger, we have no code signing enforcement on iOS, which means that this is much similar to the jailbroken case, in which interceptor can actually change and create code in memory, and so it can be used extensively. And also, Frida, in this scenario, is able to inject itself into the target, so there's no need to embed the Frida gadget ahead of time if you're going to spawn the app with a debugger. And also in this scenario, the instrumentation is quite early, so you can still capture all the early activity of the app and its frameworks with your own instrumentation. So in order to do this with Frida command line tools, you just have to get the Frida gadget from the Frida releases pages and put it in that place in your home directory with that specific name, so that Frida command line tools will pick it up automatically. So then you can spawn the app using Frida command line tools if the app is debuggable, which means it has the get task allow entitlement. Frida will be able to launch it using LLDB, inject the gadget at runtime, and detach the debugger right after that. So let's take a look at this stuff practically. So this is the app, the test app, which is very stupid. It only has 2 buttons, network and files. And this is the whole code of the app. So if you press the network button, it will make a GET request to Google using the NSURL session task. If you press files, it will open ATXT and BTXT inside the temporary directory for the app. The ATXT will be opened using the open function, and BTXT will be opened using the NSFileHandle Objective-C class. And so in terms of hooking, we want to hook so that we print the paths of the files, the full paths of those files that the app is opening. And for the network part, the hooks will be dumping the boring SSL session keys for the request. So that's it. So these hooks are very simple, but we will do this in all these three scenarios. So let's look at the code for the level 0. So the level 0 with the app is debuggable. I'm not good at typing while speaking, so I already wrote the scripts. So it starts from here. There are PC experts in it. That's where the entry point for the Frida script is. And it will call these two functions that are applying the hooks respectively for SSL and for open files. So let's start from the files. This is a simple interceptor hook. So it will just hook attach to the open export, and on the on-enter it will just get the string on the arg0 pointer and print it. In this case, log is just console log. It will become more complex later. Instead, for OpenSSL, for boring SSL, we have this, which is pretty much what you can find in Google if you search for boring SSL dump TLS keys, where we want to call this function SSL CTX set keylog callback on an instance of SSL CTX. To pass it a callback function which will be called back with a line of text which we just print. So in order to do so, we make sure the module, the boring SSL module is loaded. We create a native function so that we can call that function which we resolve using a debug symbol. Now we have to find a way to call this function on an instance of SSL CTX, and so in order to do it, we just attach to SSL CTX new. So every time an SSL CTX is created on the onLeave, we have the pointer on which we want to set the keylog callback using that function. And the callback is just a native callback, which takes two arguments. The first one, we don't care. The second one, it's a string that it's pointer to a string that we read and print. We have to keep it alive so that we make sure that the JavaScript garbage collector is not killing our callback before boring SSL wants to call it. Otherwise, it will have a dangling pointer and cause undefined behavior, which is not great. Well, that's it. So this is the whole code for the hooks of the level 0, and then we can just show this. So this device, this is my device, which is a iPhone SE 2020 with iOS 18.1, non-jailbroken. So I can just spawn the app like this, like normally, and Frida will pick up the gadget and load our hooks. Of course, the first time it fails, but that's because of the pre-warm. I have to just do it again, and it works. So now the app is being spawned and the hooks are being applied, and we already see that the app just started up, we didn't do anything, and we have a lot of noise from the open hook, and that's because we have early instrumentation and open is actually hooked in memory, so the interceptor will be hit. The interceptor hook hits for all the calls from within the system libraries that run during app startup, so we see a lot of noise. It's not important, but it's good to note because that won't happen in the next scenarios. But if I press the files button, then I have atxt and btxt, and these are the ones that we want to see, and we have the full path for them. And if I press network, we see the oh yeah, so it needs internet, but wait a second. I need to redo this by connecting to actually my hotspot. Yeah, this should work. Yeah, there you go. So here we have the keylog from our callback with all the boring SSL keys in hex. So this is what we want to recreate also on the next scenarios. So let's see. So level 1, we will have the same app, but we're not going to use the debugger. So we are going to spawn the app manually. In this case, we won't have, so we will have code signing enforced. And so this means, first of all, that we can't, we have to embed Frida gadget ahead of time because we can't create, Frida can't create or modify the code at runtime. And also, interceptor won't be able to work as it works normally because it can't change the code. And so, if we take interceptor out of the picture, we are left with function pointers, basically. But that's still a lot, because you can still do a lot of stuff with native callback and native function, because native callback still works with code signing enforcement, because Frida uses libffi closures under the hood, and that's code which is already signed, which is mapped multiple time in memories along with data pages, so that you can configure it at runtime, but the code doesn't change. And the callback implementation, it's in JavaScript, which is in fact data, so it's not a problem for the code signing perspective. And we can use native callbacks and native functions to overwrite pointers and call the original implementations, so we can still do swizzling in Objective-C methods and blocks. We can replace pointers in C++ vtables. We can replace generic function pointers in structures, and even some Swift if you're brave. But the braveness comes from the fact that you have to be careful about calling conventions, because if the function you're replacing hasn't got a calling convention supported by libffi closures, you have to bring your own translation gadgets that we also have to sign ahead of time. So I'm not going to do that in the demo, but it's totally doable. On top of this, another possibility is to use gumgraft, which allows some interceptor usage by preprocessing the binaries of the app statically before signing them, so that it can apply some of the instrumentation that the interceptor should have done at runtime, and it can't. So it works like this. It's a command line tool, part of Frida Gum, which takes a single Mako binary, and you can tell it what to hook, basically what to prepare hooks for. So you can ingest all the imports, and in that case you probably want also to transform lazy bindings in normal bindings, so that all imports are hooked the same. And also, if you need it, it's possible to specify absolute offsets from in the binary itself, or ingest all the function starts in the binary. But those two options are a bit dangerous at the moment. It can be improved because at the moment there's no code relocation implemented in gumgraft. That means that if you place hooks in the binary itself, those instructions where the hook is placed are moved away somewhere else. But if those instructions have some PC relative reference, that will get broken and cause undefined behavior. So you can do this if you know that you're not causing this problem, but in general it's very hard to know ahead of time unless you already know all or what the binary does. So yeah, it works like this. So by adding segments at the end of the binary before linked, in this way the text to data references are fixed. We just have to update the references to linked, and these segments will contain the trampolines and the configuration needed for them. much like libffi works at runtime, pretty much we do this at static time, ahead of time. And the more hooks you will place, the more segments you will have. And that's it. So if then the binaries of the app are prepared in this way at runtime, Interceptor will pick this up automatically, so you don't have to do anything different in your code, and Interceptor will work for the things you have prepared the grafting. So let's try this. But first, okay, so let's run the app for the level 1 manually. In this way, I can still. So let me show you the app. This is not this. So yeah, so this is the same code, but it will have a run script phase that runs gumgraft on the imports on the main binary. And then we have the gadget embedded here, configured for code signing required, which means that even Frida itself can't rely on Interceptor to be able to change the code. Type listen means that now I launch the app manually, but we can still attach to it using Frida command line tools. And onload resume, because we really don't need early instrumentation, so as soon as the gadget is loaded, it just resumes the app. Yeah, so we can try now to attach to it. We can see it. We see the app, which is both as gadget and as the app itself. But yeah, so I can attach to it by name. And we can try to load the level 0 hooks in this scenario and see what changes. So now hooks are applied, but if I press files, I only see A. And if I press network, I don't see anything at all. So this is the level 0 hooks with the app launched without a debugger. And that happens because, so we see ATXT, because that's the one opened directly using the open function, which is imported by the app. So gumgraft was able to pick it up, to actually instrument it. And so the hook, the interceptor hook to open will only hit for that. But btxt, even if an S-file handle uses open under the hood, will not go through the import to call open, because it's in the dyldcache. So dyldcache code calls dyldcache code directly and doesn't pass through the gumgrafted import. And so in order to still get the path from btxt, we can just use Objective-C implement to swizzle the Objective-C method. And that's good because we can, we can just, that boils down to using to use a native callback to replace a function pointer, and so we have no depth problem here. We can hook private stuff in the dyldcache in this way, and there's no problem. And so that's what I'm going to do in the level 1 for the files. So just looking at the files for now, the interceptor hook, we can keep it because this still works for ATXT. But for btxt, we can get the method that it's the one used by the app. We just save the original implementation, and then we set the implementation to a new one, which using Objective-C implement. So we can get the path again, which this time is an Objective-C object because it's an NS string, and then convert it to a JavaScript string and log it. Sorry. For SSL, it's a bit more complex. So the problem is the same. We had a hook with interceptor to hook SSL CTX new in order to get the pointer to the SSL-CTX instance, we want to set the keylog callback on, but this one is not going to work for the same reason. So it's not imported directly by the app, so Gumgraph can't do the trick, and we have to get creative with function pointers. So we have to find a function pointer which gives us access to the same instance, and that's called early enough to set the keylog callback before the handshake happens. And so, well, we don't have to look far, right? Because Boring SSL is open source, so we can just, if we look at the argument of SSL-CTX new, we see that it's a structure which holds a pointer to another structure which holds a bunch of function pointers that are very promising, especially the first one looks like one which should be called very early. And but we can see the same in R2. So let's look at this in R2. In order to do so, I have to open the dyldcache with R2. So I have here the dyldcache for this phone and this iOS version downloaded, which is also, if you're not familiar with the dyldcache, so all the system libraries in iOS are not in the file system by themselves. They're just linked all together in a single big executable that's then mapped in all the processes. You can get these, for example, from the IPSW files. And in recent iOS versions, this is also split. So like in this case, you see these are 60-something files, which contain all the libraries from iOS user space. And we can open this stuff directly using R2, using the DSC IO plugin, which I wrote. And you just have to point it to the first of the files, which is the one without extension. Now, there are thousands of libraries here, and so we, if we just open it like this, it will take a lot of time to symbolicate everything and load all the maps and so on. So there's this trick using an environment variable called dyldcache filter that you can pass. You can set with partial string matches for the libraries you're just interested in, and so that R2 will just load symbols for those and strings and so on. You still have the whole dyldcache mapped, but you will have information only about those libraries. So now if I do this, it prints all the libraries which are actually matching the filter and their direct dependencies, so that we can navigate a bit in the code. It will take some time, but not terribly much. And what happens in the end is that it's like opening a single macro executable where each of those libraries are contributing their own macro sections to the big executable we are opening. So the flow in R2 is the same as usually. So what I want to do now is to find the caller to SSL-CTX new, so that we can inspect the arguments to it and dig those function pointer that we want to replace. So what I can do, if I do IS, there are 2,000 more sections, because are all the libraries. I'm just interested in Boring SSL. So these are all the sections for Boring SSL. I don't know if you can read anything about this. I can zoom in more, but it becomes messy. But I just need the text section right now. So I can just seek to the text section and emulate it using AAEX. So this means AAEX will emulate this much bytes. $SS means section size bytes at the address section start. AAEX we just emulate for the purpose of creating the cross-references, so it will be very fast. So we just emulate this section, not all the code in the dyldcache, and so that we can find references. Now I want to find a call to SSL-CTX new, and which is this one. I can use AXT analyze X references too, and I can use the address or the flag equivalently to get the call to it. There's only one call in Boring SSL to this, and so I can just seek there and go visual and P. So, okay, so this is the call. We want to inspect the argument 0. In this case, it's just X21. So I have to figure out what X21 is. And normally do this. I highlight X21 and scroll until I see something using it. In this case, these hide registers are usually storing arguments. So I can just be confident and scroll up. There you go. So this is the beginning of the function. And we see that X21 is actually X2. So the argument we are interested in is actually the third argument to this function. So I can just, we have two references there. I can just press X and 0 to get to the first one. And so we can scroll up and see what X2 is. X2 is the result of this function call. So I can just go down there and see that this is actually creating a global reference. So basically, this argument is just an instance of a global variable, which is stored at this address. It also comes with its own symbol. And so if I go back, well, I can just do go there. Let's go there. It's not code, right? So this doesn't make sense. So I can do B and W and move to the PXR hex dump, which is the periscoping view. It's in this. So this is a bit too zoomed in to actually make anything out of it. So I can just do it here, which is equivalent PXR24. And so I can say this is. If I can compare this with this. So there's it's a pointer to this structure basically. So we get some version, then 2 pointers, and that's what we get here. So we have these null bytes, which is probably the version, and the method pointer and the X509 method pointer. So we're interested in this one, the first. So we can also go there again. And we are still in the periscoping mode, and you see that the first one is the TLS new. So this also has symbols. So basically there's this, we can just resolve this symbol by name. And we get the pointer that we want to replace, and this is where it's stored. So basically here we are in the outconst section of Boring SSL. So now we have to design our Frida script in order to find this pointer and replace it. So now we know that there is a symbol, so we can resolve this symbol, get the address, and we know that it's stored, this pointer is stored in this section, so we can use the search to do this. So we can also simulate this in R2. So if I do search in equal bin section, means that it restricts the R2 search in this current section, which is outconst of Boring SSL. So if I know the pointer to search for, I can just use the /v8 command, which means search value of length 8 bytes. So I can pass just the pointer and know that it's there. This is where the pointer is stored, which is just here, right? But this is something that we can translate directly into Frida, into Frida code. So this is what I'm going to do here. So for the new SSL hooks, so this part is the same. So we still load the module, get the native function to call, create our keylogger callback, keep it alive. But now we can resolve the TLS new symbol, find where it's stored, find the slot, which is the address where it's stored using Frida search, but we can do this exactly like we did in R2. So we enumerate the sections of boring SSL, we get the out-const range, we search it with the pattern created from the pointer we want to search for. So now that we know the pointer and where it's stored, we can just create a native function so that we can call the original one and create our callback, which I will go to the implementation a bit later. But so we have the replacement, which is a native callback, and then we keep it alive as well, and we write it. So this write pointer safely just does write pointer on this slot, just making sure it's writable first and putting it back, putting it back the original protection if not later. But so now we replaced the pointer in the structure with our own callback. So what's missing here is to know how to get the CTX from this, because this is not directly the pointer we're interested in. But it's almost that. So basically, this TLS new gets an argument of type SSL-ST, which in turn has an initializer which take SSL CTX-ST, which is what we are interested in. And if we look at this initializer by going there, P, we see that the first argument, this is a C++ method. So the x0 is the this pointer, the x1 is the first argument, which is the pointer we want. So if and we can see that it's stored in x23 instead that this pointer is in x21. If I highlight x23 and scroll a bit down, I can see immediately that here is stored in the this pointer plus 78. So if we have that pointer, we can just add 78, and if we read the pointer there, it's the pointer we're interested in. And so we can call our function set the keylogger, and that's it. So we can try this. So now the app, I don't remember if this is the right one, but okay. So the app is launched, and I can attach to it again with the level 1 hooks this time. Yeah, hooks applied, and if I press files, I see them both because we had the Objective-C trick, and if I press network, we see again the keylog. Okay, so almost there. Level 2. So now we know that we can replace pointers anywhere and not violating code signing. Problem is that if your target is capable of pointer authentication, then you have to care about how you sign them, because if you replace a pointer, you have to do it in the right way, in the same way that the caller is expecting, because that's where the verification of the signature happens. By default, Frida signs with the IA key and 0 context, but let's look at PAC real quick, just a recap. So the PAC means pointer authentication code. It's introduced by the ARMv8 specification. This is very similar. This is the same as the message authentication code as a theory. So like you have the pointer, and in order to create the PAC, you get the pointer itself, some context, a key, and create a hash using a cryptographic algorithm. That it's just a small integer that then it's prepended to the pointer itself in the highest bits, which are unused otherwise. And so then now you have your signed pointer that before being used, it's verified in the same way. So the verification happens by providing the same context, the same key, and the PAC will be computed again, and it must match. Funnily enough, this picture comes from a paper attacking it, and not from the specification itself. So that's. But so what we need to know is that so we need to provide a key and a context. So in terms of keys, we have 2 keys for pointers to instructions and 2 keys for pointers to data. They have names because these names are actually part of the instructions that have to be used to sign and verify pointers with specific keys. So we don't have access from user space to the key data. And the context itself can be anything. And so compilers get creative. And so specifically, at least on iOS, so far seems like normally C-style function pointers are fine with the default Frida signature, but instead C++ use a context which is created like in this snippet. So if you see that in the bottom it's calling a function pointer, in x8 there's a function pointer, in x17 there's the context, and the context is just the slot where the pointer is stored, blended with this small integer 6181 in this example, which is the diversity. There's even a function in Frida native pointer to do exactly this. But we have to know what is this diversity number and what key to use. And so how to do this? It's not, I mean, this stuff is, pointers are signed at load time by dyld, and so this means that this information is actually inside the dyld cache. It's not in memory though, because this information is stored in the higher bits of the pointer itself, so that at load time those will be replaced by the actual pointer, by the actual signed pointer. And that's also true in R2, because the IO plugin cleans up the pointer, and so we don't see that information even in R2. But there's a command in R2 which is able to retrieve this information by calling directly into the IO plugin. It's also possible to do that dynamically at runtime. I'm not going to show it, but you can. So this is still in the file of the dyld cache. So if at runtime you know where the base of the dyld cache is, you can just parse the metadata of the headers and calculate which specific file of the dyld cache holds your pointer, where the offset is, and go read the file and get these bits out of it. So, so in order to show this, I'm gonna use R2. We have to add one hook though, so that we can use a C++. We can override a C++ method. If we override this one, we will be able to dump the key pair used for the Diffie-Hellman key exchange. It's not particularly useful. It's just it's a good example to show. So. Let's see the app for the level 2. Okay. So this time it's compiled for ARM64E. We still have the gadget, but to spice things up now, we also have the script embedded. So we don't even attach using command line tools. We will have, so the log function is modified to use an slog, so we can just grab the syslog for agent and see the output from our agent. This is configured in TypeScript, and this is the path of the script to load relative to the gadget config. And for the rest is the same as before. So let's look at the code. But first, we have to find, let's find this. Let's use R2 to see this pointer and get the metadata. So we can use the same technique as before, actually. So we can go back to the outconst section. We can resolve that name, the symbol for that method. So if I do this, I'll see a bunch of them, but we're interested only in this one, the first one, which is the one actually called, turns out. but I can still use the V8 technique to find where it's stored in the vtable. And so this is the pointer where our pointer is stored. So if I just want to see it, is like this. But if I do :IP at the same offset, I can get the metadata about the pointer itself. So I don't know if you see this. So this is the diversity that we have to use to sign the pointer. This is the key. This is the raw pointer. This is how the pointer is actually stored in the file, in the dyldcache file, and what we would have seen here if the IO plugin didn't clean it up and rebased. So the fun thing about the diversity is that it gives us a way to find all the callers to a specific virtual method, which is not, it's quite hard to do without. And so we can show also this. So I can go back to the text section and use the /AI command, which is not artificial intelligence again. And instead means search assembly for immediate, and I can search this diversity. I'm not in the right section, of course. I have to go to the boring SSL text section and do this command again. And these are all the call sites for this specific virtual method, which if you go in one of them, it's not clear. You know, if you didn't know that this was the diversity for that method, you don't know that x8 is that specific method, right? So like, this is very useful for reverse engineering. But yeah, so apart from this, let's look at the code. So we have this log dhoffer function, which pretty much this is the same that we did so far. So we find this method pointer using debug symbol. We find where it's stored in the same way as before, just with one little change, that we have to mask the pointer. So this is a mask that will be applied to the pointer when searching, because where it's stored, it's signed differently than how Frida returns here. Because with debug symbol, we return the pointer signed with the default key and context. Instead, here in the slot is signed differently. So we can complicate this function a bit to just use the search pattern with mask, which works exactly like R2. So you have the hex of the pattern colon the hex of the mask, and the mask is computed with the one which I passed here. The only thing is that Frida is a bit picky, and it doesn't want zeros at the beginning or the end of the mask. So we have to take account of that. But that's pretty much the same code as before, plus a mask. So once we know where it's stored, we can do the same trick as before. We get the original native function to call the original. We can create our replacement as before, and then we can. But then now we have to resign it. So we can create the proper context. So we have the slot blended with the diversity, and we can strip the signature from the native callback, the default one, and replace it with the right one, with the correct context, and write it back again like before. Well, the implementation will just call the original and then dump the key pair. I'm not going to too deep into this, but basically, so the argument you have in this method is so you can just get this pointer, and at offset 8 we have the private key. And so we can use this function to get the public from the private and then dump them. So let's see this in action. So we don't have to attach. We had just to use iDevice syslog and grep for agent, and then launch the app. So yeah, so this is the pattern. I was printing the search pattern just to show. So the pointer and the mask. And now if I press network, we should see alongside the keylog, which still works because this was just C function pointers. We also have the private and the public hex dumps. Yeah, so that's, I think that's it. So. Any questions?
I have a question regarding PAC.
See? Yeah?
Beyond diagram, there is no keys, but I think there is a key.
Sorry?
In order to authenticate the pointers, there is, I think there is a key.
Yeah.
And where is the key stored and how do you get it from your script, from your system?
Yeah. So the key is, you don't get the key, you just get to know which key. You just get to know that it's the IA key, and you can get it via the IP command. Let me see if I can find it here. Here, I don't know if you can see this easily, but I can show it better. See, here. It's in the metadata of the DYD cache. So you know the diversity and the key are encoded in the higher bits of the pointer itself.
So it's the location of the key, right?
It's
the location of the key? It's the register that stores the key? Or?
It's not a location, it's just which key. Because in ARM, you just have to call different instructions for the different key. So if you know that it's the IA key, you have to use the PAC IA to sign it, or the out IA to verify it, right? You don't know anything else about the key.
Okay, thanks.
More questions? We have time.
Well, it looks like.
Big applause then, big applause.